Hi, welcome everyone. Welcome to the class on Java threads by Codecraft, the School of Code. A little bit about Codecraft. Codecraft is a school that focuses on teaching industry relevant technical skills. And at Codecraft, we also believe that coding is learned best through practice. So most of our courses have a significant portion where students do programming assignments and they do mini projects. Essentially students get to see their code in action. We provide each student with a pre-configured learning environment, which is essentially a virtual machine with all the software pre-installed, so that users don't waste time in configuring their systems. All the classes at Codecraft are taught by industry professionals who have at least 5 to 10 years of experience. The advisors to our school are Professor Amit Kumar from IIT Delhi and Dr. Sumit Sopti, who is a PhD from Princeton University. So moving to the topic for today, threads. So before we get into threads, I want to talk a little bit about concurrency. So concurrency essentially refers to doing multiple things at once. Essentially, in the context of a computer, you could think of it as a computer trying to do uh, 2 to 3 things at the same time, or even more. So one of the common things that all of you guys might have seen is that, for example, let's say you are working on a browser and you download a document, and then the download is taking long, so you switch to your word processor, and in the background the download is happening. So essentially, while you're working on your word processor, the browser is also downloading a file. So essentially two things are going on in parallel. So even though we might not be aware of it, but a computer does such kind of concurrent tasks or concurrent things quite often. So a computer typically achieves this through processes or threads, the concurrency. So the example that we talked about, that of a word processor and a browser working in parallel, that is an example of like two different processes. So each process gets its own address space. So essentially, because of this, one process cannot mess with another process. So if you have got two processes running, the chances of them interfering with each other is pretty minimal. One of the cons of creating processes is that every time you have to create a new process, it takes computers resources, and it can be a bit expensive to create a process. So the other way to achieve concurrency is through threads, and threads live inside a process. Typically, one essentially and threads will share memory with other threads. So essentially, a process is allocated a memory, and there might be 10 threads inside that process. So each thread will have access to the entire memory that has been allocated to the process. The good thing about threads is that threads are lightweight, so you can quickly create them and get your work done, and then they die. Okay. So let's see what threads are. So thread essentially inside a program represents an independent flow of control. A lot of you guys must be familiar with the main thread, which is the thread which the JVM starts when you run a Java program. So essentially, JVM starts the main thread, and that main thread essentially executes the code that you have written inside the main method. One thing that this main thread can do is that it can create other threads. Okay, we'll see some examples of that, like how we can create other threads. So essentially, whenever a main thread creates another thread, it can then start that thread, and then once that thread gets started, that's an independent flow of control that your program has. Now you have the main flow of control which was being executed by the main thread, and then you have got a independent flow of control which is being executed by another thread. So all threads in Java are instances of java.lang.thread class. Okay, and a thread starts executing when its start method is called. So if you create a thread object and you don't call it start method, that thread, the code, that thread essentially won't start. Okay, and no code will be executed by that thread, even though you have created that thread object. Okay, threads can also communicate with each other. They can signal each other, because a lot of times in a large program there are multiple threads, and when one thread is done with its job, it might signal another thread to start its job. Okay, a thread can be paused. Okay, and we'll see how that's done. And typically when the run method of a thread completes, the thread dies. Okay, so we'll see an example like how do you define the run method shortly. Okay, so how do you create threads? So that's explained in the next slide. There are two ways of creating threads in Java. So one way is to implement the runnable interface, and the second way is to extend the thread class. So let's look at the first way, which is on the left here on the screen. Essentially, here you define a class called hello runnable, which implements the runnable interface. And runnable interface is pretty simple. It just defines a method called public void run, and you have to implement that method. So in this example, we have implemented the runnable interface, and we have written a system.out.println statement inside of this method. So it doesn't do anything interesting. But let's look at what does the main method do. So essentially, main method has just one line of code which creates a new thread, and to this thread we pass a runnable instance, and then we call the thread's start method. Okay. So the main method comes in, and as soon as this line of code gets executed, a new thread gets created and it gets started, and that new thread will execute the code inside this run method. Okay, so this is how the main method creates another thread and brings it to life by calling it start method. Now let's look at the second way of doing things. Here again we are implementing a run method, but we say our class extends the thread class, and thread class defines a method called run method, which we override. And inside this method we are again doing the same thing. We are just issuing a print statement, and we print hello to the screen. However, when you see the main method, the main thread creates the thread this time slightly differently. It directly instantiates the hello thread class and calls it start method. And essentially what that does is it creates a new thread, and that thread executes the code inside the run method that you have defined in this class. Okay, and when the run method completes, that particular thread that we have created, it will die. Okay. What are the operations that are supported by a thread? Typically, let's say the main thread, let's say it creates another thread and starts that thread. Now sometimes the main thread, instead of exiting, it might want that other thread to complete its job and then do some more things, and then it might want to exit. So if you want to do this, so as soon as you call the another thread's start method, the main thread moves to the next line. Okay, and essentially it starts executing the code from that point onwards, and another flow of control is created by that thread, and that's executing the code that is inside that thread. Okay, so if main thread wants to wait before the other thread that it created finishes its job, then it should call t.join on that thread. Essentially it causes the calling thread to wait until it finishes. Okay. The other method that is supported is called sleep, and essentially if a thread wants to pause its processing, it can call the sleep method, and which causes the current thread to sleep. Okay. Another method that thread supports is called set priority. Essentially it is to give preference for execution. So threads having higher priority will be given preference over threads with lower priority by the scheduler, which is scheduling these threads for execution. Set daemon is another property that you can set on a thread, which essentially means that this is a background thread, and a background thread essentially has the property that if only background threads are remaining inside a JVM, then the JVM can exit. Okay, because their sole responsibility is to provide services to other non-daemon threads, and if those threads don't exist, then the JVM can essentially exit. Another method that the thread class supports is interrupt. Essentially, if you call this method on a thread, it will interrupt that thread and it will throw an interrupted exception. So the code that is executing in that thread should be able to handle the interrupted exception. Okay. Now let's do a quick lab. Now we have seen that how threads are created. So we'll write a small program to to create and start threads, and also we will see why we want to do multi-threading, and we'll see the impact of multi-threading on performance. So essentially we have two examples here. One case in which we will try to read the files in parallel and see if we do it in a multi-threaded fashion, we'll see some performance improvement. And the next example that we'll consider is that of a server which essentially receives requests from clients and then essentially gives them some response. So in this particular scenario, we will see what is the impact on performance of having a single threaded versus a multi-threaded server. Okay. Hi, so let's start with the lab. So essentially the first thing that we'll do in our lab is essentially we'll see uh, how the performance improves with multi-threading. Okay, so we said that there are going to be two examples for it. So in the first example, what we'll do is we will try to read data from some text files, and these text files store numbers, and the objective is to calculate the sum of all the numbers that are stored in those files. So just let's take a quick look at what the file looks like. Okay, so see here there are 10 files, like file 1 through file 10, and I'll show you the content of one of the files. Okay, and you see that they just contain numbers, one number per line, a number ranging from 0 through 99. Okay, and I'll show you that these files are pretty big, they contain a lot of numbers. So if you look at this file, it has got roughly 10 million numbers, which is roughly equivalent to like 1 crore numbers are there. Okay, and the objective is to sum these numbers up from all the 10 files. Okay, so let's look at the first program that I have written to achieve this. This is called the single thread reader. So here there is just one thread, which is the main thread, which will do most of the job. Okay, so here we make use of an object called file adder, and essentially you give this object a file, and it will essentially read it line by line and essentially compute the sum and give you the sum. Okay, so that code is written inside the get sum method. Okay, and you can see that it creates a line number reader, which essentially iterates through the line one by one, which is this line, current line equal to lnr dot read line. Then whatever it gets from there, it parses that as an integer. Okay, and then it adds it to a running sum, and finally you close the line number reader and then you return the sum. Right, so this is a helper class, if you will, which if it's given a file name and you call its get sum method, you get the sum of all the numbers in that file. Okay, so we see the main program which kind of makes use of this file adder object. Okay, so in our main thread, what we are doing is we are running a loop from 1 through 10 and creating a file adder object in each iteration of the loop, and we call that file adder objects get sum method, and we add it to the total, and then we finally print the total. Right, so essentially it's the main method which is creating these file adder objects, and it is the main method which is executing the get sum method of these file adder objects. So essentially this code that you see here, which iterates through the file, parses the file, converts it into an int, and then computes the sum. That work is being done by the main method, and it does it sequentially. First it goes through the first file, then in the next iteration it goes through the second file, and so on. So it's a single threaded program which is doing most of the stuff. Right, let's see how much time does it take to do this. Right, so let's run this application, and well, it's doing its thing. And it took roughly 14 seconds to do its job. Okay, let's try to run it once again and see what's the result this time. Okay, it's again doing its thing, and this time it took about 13 seconds. Okay, now let's look at the multi-threaded server program, which is which does the same thing exactly as this guy, but it does it in a multi-threaded fashion. Okay, so let's open multi-threaded reader. Okay, and here what you see is we have created a class called file adder thread, which extends thread, and file adder thread is given reference to a file adder object. The file adder object is the same object that we discussed in the previous example, and this thread, the run method of this thread, all it does is it calls file adders get some method, and then just returns you back essentially, and it sets the sum to be whatever result it got from there. Okay, and that's all it does. So essentially this thread runs and it essentially executes the code inside the file adder, right? Okay, now let's see what does the main method do here. So main method essentially defines a list, and we call it the worker list, and this list is empty to begin with, and this list will contain objects of type file adder thread. Now the main method again starts the same loop that we saw earlier. It iterates from 1 through 10, and for each step in the loop it creates a file adder thread object, passes it the right file adder object. It adds that thread to our list of workers, and then it calls the start method of the thread. Okay, so essentially once you call the start method of the thread, essentially a new thread is created and it will execute the code that you see here, okay, inside the run method, which means essentially it will call file adder objects get some method, which means that thread will execute this code, which previously was getting executed by the main thread. So essentially you see that earlier the main thread was executing this code. Now it's a different thread which will execute this code, right, which was the thread that we created here, right? And essentially we repeat this process 10 times. So 10 threads get created, all of them get added to this list called workers, and each of them is started, right? And you know that those threads, so main thread is not calling the get some method, but the other threads are calling the get some method. Okay, then what we do is we iterate through the list of workers and we call fat.join. What this means is that it causes the main thread to wait for this worker thread to finish. So it waits for the first one, then it waits for the second one, third one, and so on. And finally, when that gets, all of them get finished, you know, this total will contain the sum from all the worker threads. So each worker threads was working on one file, it reported the sum in that file, and we captured that in the total here. Okay, and then finally it prints the total. So let's see how much time does the multi-threaded reader take. Okay, so we go in and run this as a Java application. Let's see what happens. Okay, so this took about 6.9 seconds, which was roughly half the time it took for the previous one. Let's run it once again to be doubly sure. This time it took 7.1 seconds. So it's roughly about, you know, half the time it was taking originally. Now you might be wondering, now I've got 10 threads who are reading from these files, and I should have seen a speed up of which is, you know, 10 times the number that I was seeing earlier. But the thing is, see, this won't happen because each of these thread is reading from the disk. That's the main job. The computation itself doesn't take much time, but reading these files from the disk takes longer. And the maximum read speed that you can get from the disk is sort of dependent on the disk controller, and it might very well happen that a single thread can get a sufficient reading speed from a disk controller, which then gets distributed across 10 threads. So we might be getting a very similar, you know, read up speed. So that's why you don't see a large increment, or at least like it's not improved, the performance has not improved by a factor of 10. But let's go through our other example, which will show you, like, you know, example of a multi-threaded server where you will see a significant improvement in performance through multi-threading. Okay, so let me close these. Now let's look at a single threaded server. Okay, so here essentially this is a very basic server, and all it does is essentially it serves one file that I have in my directory. Okay, so if you look at the main method here, what we do is we create a server socket and essentially at port 8001. So essentially what it makes is that now the server is started up on our local machine, and it's listening on port 8001. Okay, and it keeps doing this forever, so unless somebody closes it. So that's why you see a while true loop here, which will essentially keep running forever. The first thing it does is it calls the accept method on the server socket, and the semantics of that is that essentially the code will wait for a client to connect. Okay, so essentially the code stops at this point of time unless a client connects at this particular port. Okay, so your code is waiting here. As soon as the connection is made, the code moves forward. Okay, we say receive the request, and after that a socket object is created when this code moves forward. So from that socket essentially is a two-way channel where people can write to it and read from it. So we get handled to the output stream of the socket. Okay, all right, and then we open a file that we want to send back to the client. Okay, I just call that file is just a text of Macbeth that I got from Gutenberg project. So I'll just send this file back. So I read this file, I create a file input stream. Now I have deliberately given here a thread.sleep of 300 milliseconds just to simulate some kind of a processing that might happen, because otherwise things were going very fast. So I just introduced an artificial delay of 300 milliseconds. Then essentially I output to the stream, since it's an HTTP request that I'm sending. So I'm sending the output back as as an HTTP response, and I write the HTTP headers here, just some basic print statements. And then the code that you see here essentially, let me highlight this. The code that you see here is nothing but we are doing a buffered reading from the input file. Okay, we create a byte array, and into which we keep reading from the file. And then what we do is, once we have got like these many bytes, like the 4 kilobytes we have read, we write that back to the output stream. Okay, which is the output stream of the socket we got from the socket output stream, right? Socket.get output stream, and essentially it writes that, and finally we close, and then the program goes, it doesn't exit, but the main thread goes back to listening for a request, and it starts waiting for another client to connect. Okay, so just to check that things are working correctly, let's just go to our browser and we will hit localhost. Okay, it says problem connecting is strange. Let's see, why is that? Oh, it will not happen because we have not started our program yet. So let's go here and we will start our program. So run as a Java application. So now our single thread server has started. So now we should be able to serve the requests that earlier it was failing. Okay, and you see here it has given the whole text of Macbeth, right? So this is our single threaded server, right, running and serving a request. So now let's do a small test with this single threaded server. What happens? So essentially it's a server that's running and multiple clients can connect to it. So what I'll simulate is I'll simulate a test where 10 concurrent threads try to get the same file. 10 clients try to get this file from the server in parallel. Okay, so I'll use a tool called Apache Bench, and I'll use the following settings. So I'll make 100 requests. So n is the number of requests that we want this tool to make, and at what concurrency level. So that we want like to simulate 10 clients. So essentially we've got 10 clients which are going to make 100 requests to fetch this file from the server. Okay, and so we'll give it the address. Okay, and let's see how much time does it take to get these files back from the server. Okay, so roughly, since each request takes about 300 milliseconds, if you remember that we had 300 millisecond wait there, so which means that one request will take 300 milliseconds or 0.3 seconds, which means 100 requests should take roughly 30 seconds, because our server is single threaded. Once it gets a connection, it sends the file, then it processes the next connection, and so on and so forth, right? So it should take roughly about 30 seconds to finish this. So let's see. You see that the total time taken for the test was 30 seconds. Okay, and an average response time becomes roughly about 3 seconds. Okay, now let's take a look at a multi-threaded server, and we'll see that how much performance improvement we get. Okay, So the code for the multi-threaded server is also here. So let's open this class. Okay. Now, so if you look here, so again, the code here is the same, that you have a server socket listening at port 8001, and then it's in an infinite loop. It accepts, and as soon as it accepts a connection, a socket is created, and it passes that socket over to a worker thread and starts that thread. Okay. So from this point of time, the worker thread is started. The main thread is now free to do whatever it was doing, and it goes back to listening for a new client. Okay. Now, and this worker thread, it had started, it's an independent control which is going to fulfill the request. So if you look at the code inside the worker thread, if you look inside the run method of this thread, it does the same thing that was being done earlier in our single threaded server, which is essentially you get the output stream, you open this input file, sleep for 300 milliseconds, and then essentially you send this output back. Right? Same thing that was being done by the other guy, but this time this code is being executed not inside of main thread, but it's being executed by a worker thread, and we keep creating these worker threads as needed. As the request comes up, a new worker thread is created, and it processes that request. Okay, so let's see how will this guy perform. Okay, so first thing we'll do is we will shut down our single threaded server. Okay, so let's stop this guy. So single threaded server has stopped. Now we'll start our multi-threaded server. So let's start this run as Java application. Okay, now our multi-threaded server has started. Now essentially again we'll try to run the same test, and I expect this time the test to finish in only 3 seconds. Why? There are 10 clients in parallel which hit our server. Each of those requests will be handled by a separate thread. So in 0.3 seconds, those 10 clients will receive the response back, because work is happening in parallel, and now each of them is making 10 requests. So 0.3 times 10, it should ideally finish in 3 seconds. Okay, so let's see whether it does or not. So same test we run again, and here we run this. Okay, there it finishes so quickly. You see that the time taken for tests is only 3 seconds. Average response time is roughly 300 milliseconds, whereas earlier it took us 3 seconds to service a request. Total test time was 30 seconds. So you could see by having a concurrency of 10, we received an improvement of 10 times in performance. So this is where, servers, if you're doing server programming, all the servers generally tend to be multi-threaded, and you can see a lot of improvement in performance when you have such servers. Hi class, so we just finished our lab, so let's move on to the next slide. So this talks about interleaving threads. So before we get into the interleaving threads, I want to talk a little bit about the multi-threaded programming that we did. So we saw that by using a multi-threaded server, we were able to get a performance improvement of about 10x in the example we saw. However, this performance comes actually at a cost, and this cost is not like a cost in terms of computing resources, but it's a cost in terms of program maintenance and program reliability. Often programs that are multi-threaded in nature, if you're not careful in programming, it can easily cause bugs in the program which are sort of hard to find. And in this slide on interleaving threads, we are going to see an example of that. So on the left side, you see a very simple class called bank account, and as you can see, this has one member variable called balance, and then it's instantiated at the time you create this bank account instance, and balance is set to, let's say for example, to 0, right? And after that, it just supports two methods. One is a deposit method, which increases the balance, and the second is a withdraw method, which decreases the balance. Okay, so let's see what a typical transaction operation, either deposit or withdraw operation, even though it's a single line, but the computer sort of does it in 3 steps that you see on your right. First, it reads the balance, then it either adds or subtracts the amount to or from the balance, and then finally whatever the new value of the balance is, it writes it back into memory, right? So let's say that two threads are trying to do this thing in parallel, which is one thread is trying to do a deposit, let's call it thread A, and another thread B that's trying to do a withdrawal. Okay, and let's say the initial value of the balance was 100. So let's see how the interleaving happens. So thread A gets a balance of 100, thread B gets a balance of 100. After that, thread A adds 10 to the balance, causing the result to become 1110, right? Then thread B subtracts 10 from the balance. Since thread B got the value of 100, when it subtracts 10 from it, it gets a value 90, right? Then thread A does the last operation, which is it writes the balance back into memory, which makes the value of balance to be 110. But after that, thread B stores this result, and it had a value of 90, so it writes the value 90, which causes essentially the balance to be 90. So essentially changes by thread A are lost, and only changes done by thread B are visible, right, to the system. Now this is just one example of interleaving, right? Now this could have interleaved in some different manner, which could have resulted in result being 110, or it could have resulted in the correct interleaving and the result could have been just 100. So really the interleaving of these operations is kind of non-deterministic. There's no way that we can say that, you know, which of these 6 operations is going to happen in what order. Okay, so this makes you wonder, like, you know, then how do I ever get it right? So the answer to that is in the next slide. Okay, so there is a notion of a happens before relationship. So if certain things happen before, then anything that happen after that point will see the result of whatever has happened before that point. Okay, so for example, if you just consider of a single thread, like you see there are program statements that thread might be executing. So here there is a happens before relationship between each of these statements in the program order. Okay, for a single thread. So if we go to the previous example once, so this whole process, let's say if it was just being done by one thread, there was only thread A there. What this would have made sure is that thread A first gets the balance, then it adds the amount, and then it stores the result back. So this would have been guaranteed, right? So if it's single thread, right? However, how do we achieve such a thing in multi-threaded execution? So there's a notion known as synchronization, and we'll talk about what synchronization means. But if somehow you are able to synchronize the operations by multiple threads, then happens before relationship can be guaranteed. Okay, and just hold on to that point for a bit. The next slide will clarify it. Okay, any thread.join operation, right? It creates a happens before relationship. So any statement that is executed after a thread.join will have actually happens after a relationship with whatever that has been happened, any operations that were done by that thread. So essentially any operations that particular thread did will have a happens before relationship with any operations that were done after thread.join. Okay, similarly a thread.start creates a happens before relationship. How? So any statements that were executed prior to thread.start would have a happens before relationship with any statements that execute inside the run method of that thread. Okay, so let's see what does synchronization means. So synchronization essentially refers to multiple threads when the things that they're trying to do are synchronized, which means something is happening before and some other thing is happening after that, right? So synchronized keyword can typically be applied to a method, and what happens is, let's say if we consider this example that we had earlier, that of bank account, I could have added a keyword synchronized right here, public synchronized void deposit, and same thing I could have done with withdraw. Now what happens is, whenever a thread tries to execute a method that has the synchronized keyword on it, it first tries to obtain a lock associated with that particular object, right? And every object has this one lock, right? So the thread will first try to obtain that lock, and if it cannot obtain that lock, it will not be able to enter that method. and it will just wait for the lock to be available. Okay, so if you have, you know, a synchronized keyword applied to a particular method, then what can be guaranteed is that that the that the release the release of these locks, right, essentially order things. So let's say first thread obtains the lock, right, and executes the method, and then after some time it releases that lock, right. Then another thread acquires the method, the other thread acquires the same lock when it executes another synchronized method of that particular object. So these two events have a happens before relationship between them. So essentially, synchronized method execution causes happens before relationships, right? And happens before relationships, these happens before relationship are sort of tied together by the acquire and the release of the lock, right? So if one method or one thread first acquires lock and then the second thread acquires lock, essentially there's a guarantee that all the operations done by the second thread will be done after the operations of the first thread were completed. So that happens before relationship is established. Okay. Synchronized word can not just be applied to methods, but they can also be applied to blocks of code. So sometimes you might not want to, you know, get a lock for the entire execution of the method code, but you might want to do it only for a small block of code. So there typically the way we use it is we make use of synchronized, not as a modifier to the method to the method definition, but inside the code we will put this line synchronized, and inside bracket you will put a reference to an object whose lock should be obtained before the block that is following the synchronized keyword is going to get executed. Okay. So now that you have understood what synchronization means and how, you know, this thread interleaving happens, let's try to see this in action and see how, you know, what kind of effects you can see when threads interleave, and then how we see that how you can fix this behavior, this erroneous behavior, by using synchronization. Okay, so let's go to the lab. So go to our IDE, right, and here what you'll see is the bank account class that we had, that I had shown to you earlier. Okay, on the slide, same thing, you have a balance and bank account is initialized with the balance. Then you have the deposit operation, withdraw operation, and get balance operation. Okay, pretty straightforward. Now when the main method starts, I create a bank account with 0 balance. Then I create a new thread called the deposit thread and another thread called the withdraw thread. So if you look at the deposit thread has reference to a bank account because that's passed when it's created. And when this thread runs, all it does is it does about 10,000 deposits to this account, each deposit in the amount of 1 rupees, right? Similarly, there is a withdraw thread which does the same thing, but essentially instead of depositing 1 rupee into the account 10,000 times, it withdraws it, right? So once we have created these two threads, we start those threads. So we assume that once those two threads have ended, ideally our bank account should have 0 balance, because we started with 0. We did like 10,000 deposits of 1 rupee each. We did 10,000 withdrawals of 1 rupee, so that should leave the balance at 0. So it starts the two threads, then it waits for the two threads to finish, right? dt.join, wt.join, and finally we print what is the current balance in account, right? So pretty straightforward program. Let's see what it does. Okay, so here we run this program. Okay, and you saw that the program ended and we ended up with a balance of minus 569. Weird. Why did we not end up with a balance of 0? This primarily happened because of thread interleaving. You know, we don't know which operation interleaved with which other operation, and they cause these memory consistency issues. Let's do one more run. Okay, oh, this time it's minus 384, a different number this time yet again. So you can see that these thread errors things are non-deterministic. You know how these things are interleaving, and I cannot reproduce the same account balance of minus 569. If I run it the third time, I might get a different value altogether. Let's run it once more. Oh, this time it worked well. I mean, you know, this time it worked fine, 0. Maybe let's try one more time. Okay. Okay, this time also it worked fine. So see, it kind of varies. I mean, it depends on how the JVM is acting. And so we are even right now. Let's try to run it once again. Let's see what happens. So this time it gave a positive balance of 1183. So you can see like this kind of thing is happening sort of in a non-deterministic fashion. Now, how do we fix this? So as you said, like if you add the synchronized keyword, let's say we add the synchronized keyword here. Okay, and we add it here as well. So what this guarantees is that at one point of time either the withdraw operation is going on or the deposit operation is going on. If two threads are trying to do the same thing at once, the use of the synchronized word will not allow this. And if that is the case, then we cannot have these memory consistency issues, because when two synchronized methods execute, so two synchronized methods cannot execute at the same point in time because they cannot execute parallelly. And by use of synchronized keyword, we always establish a happens before relationship. So deposit happens before withdraw, or withdraw happens before deposit, and they're not ever happening together, right? So let's see what does this cause, right? So let's save this program, this change, and now no matter how many times you run, you will always get an account balance of 0. Okay, 0 first run. Let's do 5 runs. Okay, if you want to run the same application again, you can just hit the run button here. 0 0. No matter how many times you run, now you will get always 0. So now we have avoided that memory consistency error. Okay, so this is how synchronized can sort of help you in avoiding these memory consistency errors. Okay, so I hope this sort of clarifies the point about what synchronized does. So now moving back to our presentation. Okay, so next thing I want to talk a little bit about is thread coordination, like how do threads work with each other. So primarily the way threads work with each other is through shared variables. Okay, and so essentially they both might refer to a common variable, and one thread might set the value of that variable, and the other thread might poll the check the condition if that condition is satisfied. Maybe maybe thread number 1 has a flag, and it sets the value of flag to true when it wants thread 2 to take over things, and thread 2 constantly keeps checking is the value of this variable 1, right? So if thread 2 keeps checking this thing constantly, it essentially causes a loss of sort of processor cycles, because it's there's a better way to do this essentially, and that better way is known as wait notify. The wait notify mechanism essentially works by causing the current thread to wait, and somebody else, some other thread, notifying it that now it can resume. Okay, so wait is typically a method. It's a method on class object, and so essentially all objects have this method wait on them, right? So whenever a thread calls wait on a particular object, one thing that the thread has to do is it should have the lock of that method. Okay, if you call wait on an object and you don't have the lock for that object, then it throws an exception. So make sure that you have the lock to that object, which essentially means that the thread should be running a synchronized inside a synchronized block, or it should be executing a synchronized method. Okay, so once you call wait, then you relinquish that lock, and that current thread goes into a waiting state. Now, how will this thread ever wake up from this waiting state? That is typically done by some other thread who also has the lock to the same object, and it will call the notify on that particular lock, okay, or on that particular object. And when it calls notify, it will relinquish the lock, and it will cause some other waiting thread to wake up. Okay, and that waiting thread will resume. Now you don't know for sure that which particular thread will resume, but at least one thread will resume. Okay, now so let's understand this concept from a lab. And here what we will implement is a bounded buffer. A bounded buffer is nothing but, you can think of it as a list that you have which is of a fixed size, and there is a producer which is putting items into that list or into that buffer, and there's a consumer that takes item out of the buffer, and the producer and consumer could be working at different rates. Okay, so for example, producer can be producing at a faster rate, So what this will cause is, and consumer, let's say, is consuming at a slower rate. So what this will cause is that this will cause the buffer to fill up. Now, if a producer tries to put another item into already filled buffer, ideally what we want is that the producer should essentially wait. It should not try to put more things into it. Similarly, if the consumer, if the buffer is empty, consumer should not try to take anything out from the buffer because there's nothing in there. So it should just wait. So this is the main thing that we will try to demonstrate through this lab. Okay. So let's go back to our IDE, and here is the code for this, which is called a blocking queue. Okay. So let's look at this blocking queue. So so let's see what's the best way. So let's look at what a blocking queue looks like, and we call it blocking queue because essentially the put and the get method that is supported by the queue, they get blocked if the queue is full in the case of put, and if the queue is empty in the case of get. So if you look at the code for the put, you see it's again an infinite loop sort of thing. When you try to put in it, we first check if the size of the buffer is less than the max size, right? If it is, then you can add whatever you were trying to put into the queue. In this case, we are thinking of tasks that are put into the queue. Producer creates the task and consumer, consumes the tasks. So it adds the task to the queue and then it notifies all, and then kind of it breaks from here, right? It exits out of this while loop, right? And also, let's say if the size of the queue is let's say it's equal to max size or it's bigger than max size, then we essentially wait. So whatever thread has called this put method, it will cause that thread to wait. Okay. How do we do the get method? Get method is done in a similar fashion. If the number of tasks in the queue is greater than 0, which means there is a task that you can get, we remove that particular task and then we exit out of the while loop. We notify any other thread which might have been waiting on this, okay, and we return the value that we have got. So key thing here is that you say that we are notifying everyone. So who might want to be notified here? Most likely a thread might have been waiting because the task might have been full, and when I removed one task from it, now we know that it's empty. So let's notify the producer that they can get it. Or it could be another consumer thread which might get notified. We don't know which will notify because there might be 10 and you took one out, now 9 are remaining. Maybe the next time the consumer thread gets notified, right? Which means that we'll take one more out, then the size will become 8, but eventually a producer will get a chance to put things back into it. Okay. Now let's see how does our main method work, which starts up this program. So it creates a blocking queue and then it creates two threads, producer and consumer. We'll see the implementation of producer and consumer in a bit, and then it just starts the two threads. Okay, that's all our main method does. So let's see what does the producer thread do. So producer thread essentially has a reference to the queue, right? Then when the run method gets executed, essentially we are putting, we iterate from 1 through 100, and let's say let's number the tasks from 1 to 100, and we put this into the queue, the number 1, number 2, and so on, right? And after we put it into the queue, I've given a random sleep of anything between 0 to 1000 milliseconds. So the thread will wait for anywhere from 0 second to 1 second, and then it will try to put another item into the queue. Consumer thread is also very similar. Instead of essentially it tries to fetch the 100 items back from the queue, and main thing is that it waits for anywhere from 0 to 5 seconds. So essentially we'll see that the producer is essentially producing at a faster rate because it only waits for 1 second or somewhere between 0 and 1 second before it puts the next thing. Whereas the consumer is pulling things out from the queue a bit slower because it waits from anywhere from 0 to 5 seconds. So what we have to make sure that our buffer does not go beyond 10. Once it goes beyond 10, we'll see that we should see this method getting printed onto the console, which means that producer thread goes into a waiting state. Okay, and every time a consumer goes into a waiting state, we put consumer thread waiting. But in our case, I think consumer thread will very unlikely that will be waiting except for the very beginning. Okay. Right. Whenever a producer puts anything into the queue, we say that I have put this into the queue. Whenever consumer gets something from the queue, we say consumer got something from the queue. So let's run this program. So we'll run it, and you see the output, how things are going into the queue, right? So you can see that producer thread has now started to wait, right? And you will see that this thing will keep on going on, because once the queue is filled up, the queue is now currently at max size of 10. You see, got 4 from queue, put 14 into queue. So you always see this difference of 10, because now producer just will wait most of the time, and because the queue is almost always full when it's trying to put something into the queue, when it's putting it at its own pace, right? So you always see that this difference is there, right? So we can just let this go, and it will go all the way till 100. Okay. So let's change this, because to make things more interesting, I mean, this will go all the way till 100, and you'll see this continuously going on. Okay. So let me just stop this program. Okay, and we'll just look at a variation of what we just did. Okay, let me just fix these things. Okay, so one variation that we can try out on this blocking queue is that, so now we know that consumers wait for a bit longer. Maybe let's start with 2 consumers. Okay, all right. So but the only thing, if you start with 2 consumers, is that they, okay, let's start with 2 consumers, and we will just change this to 50. Okay, maybe this might speed up things a little bit. Okay, now because now we have got 2 consumers who are trying to get things from. So we'll create 2 consumers, consumer 1, okay, and we'll create another consumer called consumer 2, and we'll start both of them. This is our consumer 1. Let me copy this, and we paste this back. So now we have got 2 consumers, and we'll try to get from the same queue, and we'll say consumer 1 dot start, and then we'll say consumer 2 dot start. Let's copy this guy. Okay, and when consumer 2 starts, let's see what happens now, right? So let me run this program now. Okay, all right. So see, now we are not seeing this filling up of the queue, right? Because there are 2 consumers, they are able to get 2 things now, but again we have got into that state. So this time we got into this state much later, but still you are seeing that since the consumer threads wait longer, that it still, we're running into the same state. Maybe if we have, like, 4 or 5 consumer threads, then it might, then we might, like, do a catch up. Okay, so but just so as you saw, like, from the beginning of this example, that we got into that state much later, right? Oh, sorry, I think that's fine. I think it has gone over. So let's try with 5 threads. I mean, there's no harm in trying it out quickly. It won't take much time. I mean, or we can see, like, what, let's try to put, we'll not try with 5 threads, we'll just go with 2, but instead of giving it a sleep of 5 seconds, I'll just make the sleep of 1 second. Now so both randomly wait for somewhere between 0 and 1 second. Now in this case, what we'll see is that consumer threads should get into the waiting state, because there's only one producer, but there are 2 consumers, and then they are both randomly waiting for anywhere between 0 and 1 second. So let's try to run this. This might be more interesting. Okay, so now you see that consumer thread goes into a waiting state, because most of the time the consumers are waiting, and we are able to, we are never able to fill up the queue. The queue always remains at size 1, or it's empty most of the time. And consumer threads, you never see a producer thread that's waiting. It's mostly the consumer thread that's waiting. Okay, so I hope this sort of tells you how wait and notify works, and how you can sort of create a blocking queue. Okay, so let me stop that program and let's go back to our presentation. Okay, so this we have done. So this is the last slide of my talk, and actually this talks about the java.util.concurrent package. So what we have talked about so far in our slide are sort of the fundamentals of multi-threading, synchronization, uh, creating multiple threads, locks, wait, notify, all this. So these are essentially very low level primitives. Inside Java language actually provides us much higher level primitives, so that you don't have to use these lower level primitives like wait, notify, and such things. So some of those higher level primitives are locks, semaphores, latches, thread pools, condition variables, futures, callables, atomic variables. I mean, I'm throwing a lot of names out here, but the whole point is that for multi-threaded programming, Java language has provided a lot of good higher level primitives that can be used for writing multi-threaded code. We will cover these primitives during our course. Okay, but for today, I would like to end the class here. I hope that you guys got a better understanding of threads, and now you will go ahead and use multiple threads in your program to get more juice out from the system. Okay, all right, thank you.